constructed along with the diagram, and we are left with its uses. So the uses of electric motor. So just recall the principle. The principle we know that it's a rotating device which converts electrical energy into mechanical energy, right? So the rotating devices which we can usually observe in an electrical fan, washing machine and grinder, etc. So this is used in these devices. And along with that, we need to remember some 3 points which is known as again a commercial uses of this electric motor. Let us see what are they. To get the efficient commercial uses from the electric motor, these 3 points are necessary. So let's just take a look. See the first point, we know, just imagine the diagram of electric motor. The coil is placed in between two poles of a magnet. So here the poles of a magnet are permanent magnet, but observe here an electromagnet used as a permanent magnet. So we know that the properties of electromagnet, right? So which is stronger when compared to permanent magnet. So electromagnet used in the place of permanent magnet, and large number of turns of conducting wire are placed in current carrying coil. So we just saw that a rectangular conducting wire, right? In the construction part we saw that a rectangular conducting copper wire is placed between two poles, and that coil is not just a coil, it contains large number of turns in the same rectangular shape. So large number of turns of same rectangular shape of a coil is taken here as a current carrying coil. And the next point is, as we know, what is armature, right? Armature, that is a soft iron core on which this coil is wounded. So these 3 points are important while constructing this electric motor for better uses from this motor. So you should remember, and if they ask what are the necessary points for the best use from the motor, are these. Okay. Now we know this electric motor, and in the last class only we studied Fleming's left hand rule, right? And I told to solve one in-text question. Now let us see what was the answer for that question. Now read the question. A positively charged particle projected towards west is deflected towards north by magnetic field. So deflected, positively charged particle towards north, the direction of magnetic field. So we need to find out the direction of magnetic field. We'll just draw the directions. So let it be north, east, west and south, right? So look at the question. A positively charged particle, that means current. Positively charged particle is nothing but current towards west. So this is the direction of current which they are given, and it is deflected. So what will be deflected? The force from the magnetic field. So if this is our Fleming's left hand rule, the middle finger indicates current which we have here, and the thumb finger which indicates the force of motion, right? So here it's towards the north. So this is force. And next one we have the direction of magnetic field which we need to find out. So here we have an option C, towards south, towards east and downward and upwards. Now apply the Fleming's left hand rule, take your left hand rule, and this is current. So how you should show? This is how, right? So this is how the current is flowing. So for just to understand you, let me write this one. This is north and this is south. Let us take this as the west and this as east. Here the current is flowing, right? So this is the current, and this is what? The forefinger. The forefinger shows the direction of magnetic field, right? So this is upwards, and again here the force. This is also showing upwards. So both force and magnetic fields are upwards. So hence the answer is option D. I hope you understood. So here I can't should apply like this. This is current and here also showing like this. So no need to write this one like this diagram only, just for to show the Fleming's left-hand rule. I wrote this diagram. So this is the answer. So while writing in your notes, you should write this one also, because later you will forget, and based on this one only you can easily remember at the end also. Now students, let us start the new topic of this chapter, that is electromagnetic induction, which can also called as EMI. So EMI, electromagnetic induction. This is one of the important topic of this chapter. Till now whatever we studied, there we'll get a direct question. Only under this concept we can accept an indirect question. So understanding the concept is important to answer a question from this topic. So try to understand the concept, okay? So here electromagnetic induction. So we already know that Michael Faraday, right? So he is the person who discovered this theory, electromagnetic induction, and he is also known as father of electromagnetism. What? Father of electromagnetism. So here you need to write down in your note, that is important. So the first, in the beginning of this chapter we got one scientist, that is Hans Ørsted, and here we are knowing about Michael Faraday. So you will get multiple choice question based on these two scientists. So here I repeat again, remember Hans Ørsted is the person who gave a link between magnet and a current. So in the question we can observe the word link between magnet and electric current. But he is the one who gave the theory of electromagnetism, and he is also known as father of electromagnetism, and he is the one who discovered electromagnetic induction under this magnetic effect path. So now let us see first, based on his activities, he gave a definition for EMI. So first let us take a look of the definition. So first, by taking a look we won't understand, but the definition is based on two activities. So first let us take a look about definition. Next we'll see based on what activity the definition is given for EMI. So the definition of EMI is when a current is placed in a changing magnetic field, some current is induced in it, and such current is called as induced current, and the phenomena is called as electromagnetic induction. So I'll repeat the statement again. When a conductor is placed in a changing magnetic field, some current is induced in it, and that current is called as induced current, and this phenomenon is called as electromagnetic induction. So in the same definition we have two parts, that is the first, some current will be induced, and that is called as induced current, and the entire phenomenon is called as electromagnetic induction. Now the same definition we will once again recall later after understanding activity 1 and activity 2. So to understand or to know this definition of electromagnetic induction, as I told, based on two activities he defined the whole thing. So let us see first activity. Okay, before that we need to know one term, that is galvanometer. Galvanometer, which is indicated as G. Okay, has a meter, as voltmeter, same thing. This is also one of the components of a electric circuit, that is called as galvanometer. The role of galvanometer is it shows the presence of current in a circuit. So if we have a galvanometer, it shows there is a current in circuit or not. And one more property of this galvanometer, at the same time it will show the direction of galvanometer. So this is a device. So here we have a meter, here we have maybe some 10, 20 like this. Okay. So if this deflect towards this, it positive or negative. If it deflect like this, then it is the direction of current is in the right, and if deflect like this, then the direction of current towards left. So the galvanometer, which shows the presence of electric current in a circuit and the direction of current in a circuit. So this is the role of galvanometer. Here Michael Faraday took one coil. So this is our first activity. He took one coil, and to that coil he connected galvanometer. To that coil he connected galvanometer. Okay. And the next part is he took one magnet which has north and south poles. Right. Now all he was expecting is there should be a current flowing in this coil. But remember, here we don't have any battery or a plug key. We have only galvanometer which shows the presence of current. We don't have battery, and we know that without a battery we won't get any electricity. But he was expecting the presence of electric current in this coil. So he took magnet and he kept aside. So if it is fixed, then it is called as stationary. Okay. So he kept a magnet stationary. He didn't find any electric current. So the next step what he did is he started to move this magnet towards and away from the coil. So when he started to move the magnet towards and away from the coil, he observed that the deflection of needle. So he observed the deflection of needle in a galvanometer, and which indicates there is a presence of current in this coil. So here what he was expecting, that came true. And so now what was the thing happening is here, whenever this magnet is moving, there will be, as we know, the magnetic field lines are produced, right? So magnetic field lines will produce, and this magnetic field lines link with this coil. And whenever they start rolling, we will get an electric current in this circuit. So this is his first activity. So by the deflection, by the movement or by the motion of the magnet, the current will produced in this coil, and that produced current is called as induced current. Now I hope you understood. So now let us come back to the statement. When a conductor is placed, so here conductor is placed, so this is our coil. Conductor is placed in a changing magnetic field. So here we have a magnet which is keep moving. Whenever we keep moving, the magnetic field lines will be changing. So when a conductor is placed in a changing magnetic field, some current is induced. Induced is nothing but produced also. Okay. So some current is produced in this coil, and such current is called as induced current. So from this first activity we understood the current is produced with the motion of magnet and with the help of these magnetic field lines of this motion of magnet, and that current is called as induced current. And remember, if this is fixed in a position without moving, in that time also it will get magnetic field lines, but there will be no change in magnetic field lines. So when the magnetic field lines are stationary, we won't get current. So this is what we understood from this first activity. And at the same time, here we need to remember one more thing, that is, so when we started to move, so let us assume this as A and B, end of these coils. When the magnet started to come towards the end of this B, towards this coil, it shows towards the direction is right side. So the deflection is shown towards the right side. And when this magnet, so suppose we have so if this is a circular, we have a place inside, right, in a cylindrical shape. So this is started to move from here, that is started to withdraw from this coil. So when the magnet came here, so we don't get any deflection, that is G will be 0. That because when both are kept at stationary, we won't get any induced current. Only in the moving magnet will produce different magnetic field lines, and then only we will get deflection in this galvanometer. And when the magnet is started to move away from the coil, that time we got the direction opposite to the first one. That means here we will get that is left hand side. So left side. So just imagine we have 3 steps here. The first one is here, and the second step here, and the third step is here. That is when it's coming towards the coil, and when it is kept stationary inside the coil, and when it is moving away from the coil. So what happens when it is coming towards? The galvanometer shows right side deflection. And what happens when it is inside the coil? No deflection, because both are stationary. And what happens when it's moving away from the coil? Then the opposite direction, the first part, that is left deflection in the galvanometer. So this is all about activity 1. Now let us see what is activity 2. So here, again Michael Faraday, he took one cylindrical coil, not a coil, a cylindrical device or anything. On this, he took a coil, 2 coils. So one is connected to galvanometer and another one is connected to battery and the plug key. Now just look at this diagram again. So the construction part of activity 2 is, here we took one cylindrical coil, and in the same cylindrical coil we have 2 coils. So let it be coil 1 and coil 2, and this one is called as primary coil and this one is secondary coil. So look at the board. So here we have a number of turns in the first coil, and which is connected to a battery and a plug key. And here I am just showing only some 3 to 4 type of turns, but imagine in an actual experiment it will be more than 50. So minimum 50 to 100 it's must and should. In one coil it should have minimum 50 to 100 turns, so which are connected with the same cylindrical roll. Okay, now we have 2 parts, and in the second coil, the coil terminals are connected only to galvanometer. Now here, according to Michael Faraday, so when we switch on here, what happens? The current will start to flow in this first coil, and from hands-on state experiment we know that any current carrying conductor will produce magnetic fields, right? So the first activity of this first chapter, we are connecting here, any conductor carrying electricity will possess magnetic field lines. So when we switch on here, the magnetic field lines will link with this coil, and we can observe the deflection in this galvanometer. So again the current is obtained in the coil 2, and that is called as induced current. So here we need to learn 3 parts. So let me write here. So when we switch on the coil 1 setup, what happens? A momentary deflection, that means a deflection will go and again it will come back. Like a momentary deflection we observed in the coil 2. And again when we switch off the current, what happens? This coil will act as a artificial magnet. No magnetic field will produce. But when we switch off the current also, we observed momentary deflection in the galvanometer. So when we switch off, so there is a deflection in galvanometer. Then we switch off and switch on. But when we kept current in steady, that means we on the device and we kept with some steady volt or ampere, and that time we observe there is no deflection in the galvanometer. So let me repeat. What happened when we switch on the current? Suppose we have some 2 ampere in this current. So 2 means it will start from 0 to 1, then 1 to 2, right? Like from 0 means 0.1, 0.2, 0.3, like that we will get till 2 ampere. So when the current started to flow from 0 to 2, when it reaches base 2, what happens? We get 0.1, 0.2, 0.3 like that, different numbers, and in each cases we will get different magnetic field lines, and we know that induced current will be produced only when we will get the different magnetic field lines. That means the magnet should possess its motion, and that time we will get different magnetic field lines. If the magnetic field lines is stationary, we won't get any deflection, which we studied in activity 1. So when we started from 0 to 2, we will get number of deflection in number of different magnetic field lines, and hence that will link with this coil, and we will get deflection in galvanometer. And the same thing when we switch off the circuit, it should come back from 2 to 0, right? The reverse order, it should come back from 2 to 0. It's just example for understanding purpose. So when it come back from 2 to 1, it will come back at 1.9, 1.8, everything it reaches, and each and every point we will get different magnetic field lines. And when we get different magnetic field lines, it will show a momentary deflection in the galvanometer. Now we understood how we get deflection in both the cases, when we switch off and switch on. Now what happens when it is steady? When it reaches 2 ampere and it will fix to 2 ampere, it won't decrease or it won't increase. That is called a steady current. At the steady current, there will be no change in magnetic field line. Suppose if this is a steady current and this is a magnetic field, both are will be same. Magnetic field also won't change, steady current also won't change. When the both of cases are at stationary, what happens? There will be no different magnetic field lines, and when there is no different magnetic field lines, we won't get any deflection, which we already understood from activity 1. So this is process what we understood from activity 2. That is, when the switch is on, we will get deflection. When we switch off also, we will get momentary deflections. But with the steady current, we won't get any deflection in galvanometer. And this phenomena or this process of induced current with two coils in the same coil is called as EMI. That is electromagnetic induction. Now we understood both activity 1 and activity 2. Let us come back to the definition of EMI. When a current is placed in a changing magnetic field, some current is induced, and such current is called as induced current. And the entire phenomena, what we understood from second activity, that is called as EMI, electromagnetic induction, which is important. And remember, if they ask this part, you can't write on your own. You should make sure to use all the terms, so exactly reproduce as it is. Okay. Now let us understand some of two concepts to answer some of the multiple choice question under this concept. Here we are learning some rule called as clock rule. It is not in the syllabus. It is just an additional information. So if you understood some of the two concepts, this is, and one more I will cover after this topic. If you understood those two concepts, it is easy for us to solve some type of multiple choice question, which I will explain later with an example. So this is a clock rule. So we know that if this is our coil, it will act as sometimes a two poles, that is north pole or a south pole, and there we should know the flow of current. So when there is a flow of current, there should be a direction of current also. So know the direction of current in each side of a coil. So this rule is easy to understand. So I am taking two coils. So it in the case like this is from one end of a coil and this is another end of a coil. So here, if current started to flow in anti-clockwise. So this is just a trick to remember, okay? So if current started to flow in anti-clockwise, that means just imagine like this. That means it's flowing like this, right? It's flowing like this, and later it's coming back like this. So why I wrote exactly like this means something we have two poles called north and south. So which is, this one is looking like north, right? So this looks like a north, which shows the current is flowing anti-clockwise. And again while coming back, it is like this. So here anti-clockwise. wise. So since it represents a N symbol, just for our assumptions to make some tricks for easy understanding purpose, we are writing this one. Okay, so this indicates North Pole. So in a North Pole, we can directly say that the current will flow in anti-clockwise direction. And here, when it comes to the another pole, south. So if it is anti-clockwise, let us take this is flowing clockwise. So this is clockwise. That indicates. So yes, clockwise motion. Understood? So this is goes like this. So like this. So here it's flowing clockwise in south pole. So this is what we need to remember. Just write somewhere as a note. Okay. So we have two ends. In a north pole, we can understand the current will be flowing in clockwise direction, and in a south pole, it's flowing in. Sorry, here in anti-clockwise and here in a clockwise. And this is practically proved also. When we take that solenoid or a circle of coils, when we look from some of the angles, the shape it will look somewhere like a N, and some in the south some of south pole side it will look like a S only. So based on that, they made this trick as called as clock rule. So now all you need to remember is in north pole the current will flow in clockwise direction, and in south pole it is flow in here anti-clock and here clockwise direction. I repeat, in north pole it flows in anti-clock, and in the south pole it flows in clockwise direction. This is clockwise direction. Next, one more rule we have. Again, it is not in the syllabus, just an extra information, that is called as Lenz's law, which is there in a PU syllabus. Just will understand what that concept will tell. So let us see what is Lenz's law. Now see Lenz's law. So what Lenz is a scientist, what he told is an induced current, I represents the current, an induced current generated in a coil will be in a way that it will oppose the reason what actually caused it to happen. So here you don't need to remember this definition because out of the syllabus. Let me explain now. If this is our coil, so here an induced current is obtained, right? So when there will be a different magnetic field with the motion of this magnet, the induced coil will obtain, all we know in the electromagnetic induction. So the next step is, so when that induced current is obtained, it will oppose that one. So actually it will oppose the reason why that induced current is obtained. So just remember here. So the thing is, if this is north and south pole, to actual process to take place, what here he mentioned, it will oppose the magnetic field lines of this magnet to produce the property. So to oppose this one, so here just all you need to remember is oppose the reason what actually caused it to happen. So if this is north, when it started to come near this coil, it will oppose, and that is the reason for actual cause. So it will act as it is opposing. So just recall the magnetic property. When magnets will oppose is nothing but repel. So when the like poles will come, it will oppose, it will attract with only unlike poles. So to oppose, it should act as a north pole. That means from this we can understood if this is north, it will be south. So from based on this we can give the poles to this coil. So if it is north, it will started to come here, and it will also act as a north to oppose. For example, if it is south, if it is north, what happens? If it is north and south, it will attract. But here what he told, to actual cause, it will act as a opposing. So it will also act as a south and it will oppose. So this is all about Lenz's law. I will repeat. An induced current generated in a coil will be in a way way that it will oppose the reason what actually caused it to happen. That means to oppose that one, this end will also act as a same end of this magnet, just for to oppose this one. Okay, so if this is north, it will also act as north, and if this is south, this will also act as south. So based on these two laws which we learned, that is clock rule and one more, this one is Lenz's law, let us solve one multiple choice. Later on we will get some of the questions similar to this one. For the question, if a south pole is approaching a coil, then the direction of the current at the coil end is what? So this is the question. So now I hope you understand both Lenz's law and clock rule. Based on that, try to answer this question. So take your time, try to analyze that concept and try to answer this part. See, a south pole is approaching a coil. That means we have a coil and this is a magnet, and south pole is approaching the coil. So this is the first statement. Then the direction of the current at the coil end. So since we have taken this side, we need to find out the direction of current in this coil. So this is what they are asking in the question. Now let us apply first, which one? Clockwise rule here. Both clockwise and Lenz's law. When south pole is approaching here, to take part of what actually the process happens, what happened here? This end will also act as south pole to repel, to cause the exactly what should happen. So it will also act as south pole, right? So when it acts as a south pole, what is the direction of current here? Now use the clockwise direction. If it is south pole, it will be clockwise direction. The answer is the direction of the current at the end of this coil is clockwise. Now I hope you understood what type of a multiple choice question you will get, and based on clock rule and Lenz's law, how you should answer that one. Okay. Now let us see what is Fleming's right hand rule. In the last class we studied about Fleming's left hand rule. Here the same thing in a right hand. So take your right hand. So same thing here, stretch each finger perpendicular to one another. Here the middle finger in the left hand rule, it was representing current. So here also same, but here it will represent induced current. So the difference is their current and here it is induced current. And forefinger same, that is magnetic field, direction of magnetic field, and thumb finger force or a motion. So same thing we can remember, FPI, induced current. So here if this is middle finger and this is forefinger and this is thumb finger, forefinger and middle finger, here it will represent the direction of force or a motion, which is thumb finger, and this one forefinger represents the direction of B. B is what? Nothing but magnetic field. And here we have middle finger, which represents the direction of induced current. So what is the use of this Fleming's right hand rule? From Fleming's right hand rule, we can find out the direction of induced current. So based on this, we have one more topic, that is electric generator. In the last class we studied electric motor, which is work based on Fleming's left hand rule. Now we have electric generator, which works based on EMI principle, and in a EMI we will get induced current, and to find out the direction of induced current, we will use Fleming's right hand rule. And before going to electric generator, as I told, in the EMI topic we will get indirect questions. Only if you understand the concept we can able to answer. So let us solve one question for 4 marks. Okay. So look at the question statement. This is not yet question, just the beginning statement. The given figure shows coil connected to center 0 galvanometer G. The galvanometer shows a deflection to the right when the north pole of a powerful magnet is moved to the right as shown. This is a statement of a question. Based on this, they will ask 4 questions. So in almost all of the different questions also we will observe, first they will give a statement, Based on this concept only they will ask the question. So we should understand this concept, then only we are able to answer the questions. So all they explained is when the magnet with the north pole end is when started to move towards the coil, the deflection in the galvanometer shows towards right, which we already know. When you move, when this magnet moves away, what happens? This will show left deflection. Now in the question they only told when the north pole end of a magnet when started to move towards the coil, the galvanometer shows deflection towards right. And this is a question. Now let us see what are the sub-questions from this statement. First question, explain why deflection occur in galvanometer. So these questions for 1 marks each, that is overall 4 marks question. So explain why deflection occur in the galvanometer. They already explained the process, what's happening here, and they are asking why the deflection takes place in the galvanometer. So what is the answer? All have only one word answers. So here we have a magnet. We will get magnetic field lines when we started to move, different magnetic field lines that will start linked with coil, and here the current will form, and that current is called as induced current. Hence here the deflection shows in galvanometer, which we know, but we can't write everything. So what I explained now, the entire phenomena is called as what? Electromagnetic induction, right? Therefore the deflection occur in galvanometer due to the phenomena of electromagnetic induction. So only one word answer, that is due to electromagnetic induction. And the next question, does the direction of current appear clockwise or anti-clockwise when we viewed from the end A? So here they named this coil end A and end B. Once again read the question. What they are asking, what is the direction of current when we viewed from end A? So when we take this end, that is A, what will be the direction of current in this part? Whether it is clockwise or anti-clockwise. Now here apply both Lenz's law and clockwise direction. They are already telling north pole of a magnet is moving towards the coil A. So when it's moving towards, what happens this coil? To repel this magnet, it will also act as north. And when it is north, the direction of current is anti-clockwise direction, right? So hence the answer is anti-clockwise direction. And the next question, see, state the observation in galvanometer when coil move away from north pole. So this is a coil. We need to observe the galvanometer, what happens when it started to move away from the north pole. So what I told, when north pole is moving towards the coil, we will get right deflection, and when it is moving away from the coil, we will get left direction. And I mentioned when the magnet is moving, but it is also same. When we kept the magnet here, and if we keep moving coil, both gives the same picture. So both give the same scenario of same process, right? So here when coil is moved away from a north, that means north is going away, the magnet is moving away from the coil, that means it will show the direction of left side. Okay, so I hope you understood this point also. Hence the observation in galvanometer is the deflection towards left side, right? Now the last question is same. State the observation in galvanometer when both coil and magnet moved to the right with same speed. So this is magnet and this is a coil. If this is right side, both move towards right with the same speed. Now what happens to the galvanometer? So any guesses? Think yourself and try to answer. When they both move in the same speed, neither the magnetic field won't change because it will move with the same speed, and this is also moving. When this is stationary and this is moving, what happens? We will get different magnetic field lines. When both are moving at the same speed, that means both are in a stationary mode, but they are moving but what they produced, magnetic field, and here when it linked with a coil, it will be stationary. So what happens? The galvanometer shows zero deflection. So in the galvanometer we saw zero deflection, and this is similar to activity 2. That is, when a current is steady, what happens in a coil 2? So what happens when a current is steady? The galvanometer shows zero. So suppose this is my magnet and this is this is coil and this is magnet. When the both will move, we won't get any different magnetic field lines respect to this coil. That means no induced current, magnetic the deflection in a galvanometer shows zero. Now I hope you understood both the questions. So to understand this, you should know already what happening in activity 1 and activity 2, and this is how we will get different type of question for 4 marks from this electromagnetic induction. In the similar way, I will give you the homework, try to answer them also. Now in today's class we understood electromagnetic induction as well as right hand thumb rule, that is Fleming's right hand thumb rule. Now based on this, we should see what is electric generator, as it is principle, working and construction. In the next class, let us see about electric generator and AC current, that is alternative current, and DC, that is direct current. So understood this concept and try to answer all the homework questions. Thank you.